So, like I said, there is instead of an attendance score. So we talked about the exam, the possibility of second midterm, because I won't be here anyway on next Thursday. But there were mixed feelings. People, some want like it. Sometimes I was listening back to the video. It was hard to tell what was the thing. And of course, we had discussion after that too. So you know how things are. And I asked you to just vote one way or other. And it's like a huge amount of work for us. You actually have to do the test. And so it's really not worth it if people are more or less prefer, for whatever reasons, good or bad reasons, that they would just do the final exam. It's completely fine. So what would happen then, of course, is I'll just let you know. I mean, this was not a. I have to count the numbers because this is an actual short answer question. I'll let you know what happened and what we decided once we. So. Even people who are not in the class hopefully should vote. And it would be on your name, so it's not an anonymous poll. I expect that people will vote their self-interest. That's completely fine. If you're done well in the exam and you don't want another exam, that's completely fine. Voting is always that way. Everybody votes their self-interest. Yes.
So if someone doesn't vote, do not count their vote?
No, I mean, basically, again, decisions are made by those who show up, right? That's the definition of democracy, so decisions are made by people who show up. Yeah. Yeah. No, it's only one way or other. It's only one way or other. Yeah. Well, can we have like some days Trump, some days Hillary Clinton? Really happy. If you can make that happen, I do this. Like maybe at least the best course, some places different presidents. Anyway, that's not getting. Yes.
So is there any what's the expectation for the second midterm?
It would be until the end of today's class. Yes.
As you said, there will be overlap between the previous.
Yes. Yeah. That was the whole point. So that we get it for that. Yeah.
Whole midterm one plus.
Plus. Yeah. Exactly. Okay. Any other questions? Yeah.
Did we talk about the way that it would all be weighted and scored? And
Actually, speak louder.
sorry, did we talk about if a second midterm how it would be weighted and scored based on numbers?
It would be sort of another midterm, so it basically be weighed along with other midterms.
Okay.
That's the way it is. Yeah. So that's right. Yeah. No, I think it will be one way or other, and we will basically look at it. I mean, it's not, unless it is like overwhelmingly one way or other, we might decide to save our time. Okay, so it's like actually a lot of work for us to set the exam and for them to actually grade it. So if it is not a overwhelming one way or other, then we get to decide after that. So I actually think that's also a good idea for presidential elections. After the elections come over, you'll say, for the next 4 years we won't have a president. That'll be fine. And because if you can't be sure, then you should do that. I think in parliamentary democracy that happens. I think Israel has just, for the third time or so, cancelled their government. Belgium for like many years didn't have a government. Nobody noticed the difference. So in fact, the chocolates were just as good. You never know. Okay. So what I'm going to do today, basically, turns out is I'm going to actually continue doing the discussion on planning that we started last class. I sort of changed my mind. I was going to just do that, only that piece, and move on to something else. But looked like at least the people who were there had lots of interesting questions, so I thought I'd do this. It connects back to the A-star search view of problem solving. So in some interesting way, there's like a nice connections that you can make with respect to what you learned here and what you learned there. And so that's what we'll do. As I said, the chapter 10 is mostly what we covering. I'm just going to go quickly over the parts that we've already done, but then mostly look at additional ideas that we will be discussing. In general, the basic top-level idea is that A-star search required like a child generator function and a goal test function. And then the search essentially basically just called child generator as needed, goal test as needed, but then manage the queue itself using the F values, D values. And of course, if you're doing A-star search, you also need an edge function, which you can apply to any node and say how far are you from the goal node. Okay, the difference that when we come into this, what we are calling planning here is operator planning is probably another way. There are multiple different ways that people have used for this. The word planning has been used in multiple different places in this course too. In general, if you ever have an atomic model and you're doing search on that, that's been called planning. In reinforcement learning, model-based reinforcement learning essentially does planning on the model. Okay, but that's basically search. Okay, so the same search here, instead of doing it at a A-star level, we do it with operators defined in terms of their preconditions and effects. Okay, and it's a lot more natural way of thinking about actions. So one of the interesting questions would be if computers, if machines come up with theories of how to do planning in a domain and also generate plans, you don't really care how they thought about the actions. If on the other hand, there are lots and lots of domains where you know how to actually solve the problems, you know what are the relevant actions, what are not the relevant actions, and what you would wind up doing in that case is essentially write these actions yourself. And writing actions is much simpler than writing child generator function and goal test function. So if the actions are in the same format, in this precondition effect format, then there is a generic child generator function and a generic goal test function. And that can be used anytime the domain is in this format. Okay? So it's like a way of writing the operators, a language for writing the operators. Okay? So that's what we're going to be doing here. So that's what search with state variable models is. And then we talked about an example. Essentially, there are state variables on table. Basically, these are, I'm assuming, I have to make an assumption that people who left before the extended session actually watched what happened. So we talked about the stuff there, that there are state variables, and the actions are written in terms of the preconditions that must be true and the effects that will be true afterwards. And the preconditions as well as effects are essentially what are the preconditions say certain state variables must have certain values. These are all Boolean state variables. So this one is saying to be able to pick up X, hand empty must be true before, clear X must be true before, on table X must be true before. And if that is the case, then in the new state, the state after the action, it will make sure that holding X is true, not on table X is true, that means basically on table X is false, and hand empty is false, and clear X is false. Okay, so this is sort of, you can almost make sense of what the clear pickup action is doing. And this is how you can take a new domain and write a domain model for that. We'll see some examples that people do. There's actually a language for this, for writing these kinds of things that we'll see in a minute called PDDL, which is planning domain description language. And so you get to pick whatever domain you want and you just write the actions in terms of the preconditions effects for that. And so this is you giving knowledge to your machine. Okay, and then the machine does the search. Remember, that's more or less what you did in the A-star search too. You gave the knowledge about the search, the problem, like whether it is a Pac-Man problem or something. You decided what the child generator function is and what the goal test function is. Here you're sort of streamlining them, into a particular kind of a language. Okay, so we talked about in this particular case, essentially there are like two blocks, A, B, and there's a hand. And if the block is being held, then essentially you call it being holding block. And if the block is on the table and there's nothing else on top, then it's clear and it's on table. That's the general physics. Okay. So in some sense, you can think of this is basically the physics of the domain. People actually use this word, domain physics. Transitions, right? Basically, the actions are transitioning states to other states. Okay. And so you are talking about the domain physics as you understand it. And so there are like 4 actions I wrote here: pick up, put down, stack, unstack. And then I have an initial state where A is untable, B is untable, A is clear, B is clear, and is empty. And the goal state, I only give not clear B and empty. Notice that in this particular kind of scenario, if A and B are the only plots, only objects, then you have clear A, clear B. You have on AB, you have on BA, you have on A table, you have on B table, you have holding A, you have holding B, you have hand empty. 9 different propositions that can be true or false. You see what I'm saying? Just 9 different propositions that can be true or false. So a complete state tells you which of these variables are true, which of these variables are false. A goal state basically tells you what are the variables that you care about and what their value should be. And there may be many, many states where those variables have those values, and all of them are considered goal states. This is more or less is what happens when you have goal test function, right? So basically, we played with these 2 games. A star search was seen as if it was a graph search. And if it's a graph, there is an actual node, as a start node, a node, as a goal node. Okay, but really, A star search was implemented as an implicit search, where the graph doesn't exist in front of you. You only are given the initial node, which is the initial state. There is a child generator function that you can call, it will tell you what are the children. And there's a goal test function that you can call, which says, yes, you're done, or no, you're not yet done. Now, nobody ever told you that the goal test function will say yes only for one of the nodes. It could have said yes to many, many nodes. Do you see what I'm saying? In fact, optimal path essentially is telling you that there are multiple goals, and the one that you can reach with the shortest, cheapest actions, cheapest sequence of actions is the best path. Right? So in general, goal test function tells you what you care about. I went on and on last class about the fact that you may have your current initial state, which is defined in terms of your complete configuration, in terms of the shirts you wear, your length of hair, etc. And the goal is pass the class. And it's not that you won't have hair by the end of the time. No, it's not that the hair is not a variable when you pass the class. Okay, I don't care whether you have hair or not hair. I don't care whether you have a shirt or not shirt. Okay, I only care whether you passed or not. Okay, so goals are basically always partially specified, right? And that's just a normal thing. And in a way, that basically is what's being allowed here. And then, so a special case of this is the one that I wrote here. This is directly from propositional logic. Because in essence, you allow literals. So preconditions can be literals, effects can be literals. A literal is a proposition or a negation of a proposition. Do you see what I'm saying? Historically, the original, in fact, the AI kind of robotics revolution, etc., started with STRIPS, which is Stanford Research Institute problem solver. And they had essentially this, clumsy robot called Flaky, appropriately named, and that would do things. And it is in this Flaky project that a whole bunch of ideas were invented. A star search was invented as part of Flaky project. Okay, planning like this was invented as part of Flaky projects. Okay, and in particular, that particular problem solver that Flaky used was called the STRIPS problem solver. And STRIPS has been used for a particular kind of search, also as a kind of a language for writing actions. So the STRIPS language this is the language that I showed you. So put down X has precondition holding X, effect on table X, hand empty, clear X, not holding X. So effects and preconditions have literals. STRIPS, for whatever reason, decided to only think in terms of positive literals. So if you're doing something useful, then you're making something true. Okay? And then basically it will assume that the preconditions are always positive literals, and effects are also positive literals, and then the effects are split into two subsets, add and delete lists. Add list basically makes something true. Delete says what if it is true, just make it false. So it's a syntactic distinction. Okay, so in general, you're more likely to think, people tend to think sometimes in terms of add and delete for actions. You know, what does this action make true, what does the action make false? It's not necessarily the case that all goals are positive, but in strips they are. In strips, goals are always positive, preconditions are always positive. Okay, don't destroy the world is a very noble goal. You see what I'm saying? Not destroy the world is a very noble goal. Strips won't allow you to say it. Right? Then you have to come up with a new proposition, essentially, called not destroy the world. Okay, and then write it as a qualification. In general, you can often compile this representation to this representation. Okay, we'll talk about even more interesting representations in the same direction, but you know, I use this because it's more general, a little more general, but this is what textbook actually talks about in terms of add-delete list. I mentioned PDDL language. So the language looks in this format. I'm not actually trying to teach you the syntax, but I'm just saying they will give you for any given domain, this is basically this domain called gripper domain. There are two rooms, there are some balls here, and you want to get all the balls from one room to other. And then this robot has two grippers. Okay, so the optimal thing would be to take two balls at a time and move, instead of taking one ball at a time and move. Okay, it's a very, very simple domain. And then essentially there is some sort of a formalization of the domain in terms of writing the state variables for the domain. You have an initial state and you have a goal state. So basically goal state says all the balls should be in room B. That's what it's saying. Okay, and then basically it defines the actions sort of the same way, precondition and effect. In fact, they're using effect rather than add delete. Okay, but PDDL actually also allows strip style actions to be represented if you want. This is just to say that you can write actions this way, and there are planners out there that can eat these actions and generate plans for you. You see what I'm saying? So, but how those planners work is what we are discussing. The same thing, I mean, neural networks, there are keras where you can just specify the network without understanding whatever the heck happens, right? And it all just gets done. And the difference between people who are using it that way and you hopefully is you have some idea of what actually gets done. Okay, and that's what we're going to do. That there are planners which can take domains written in this language, where the domains are written by humans. So they have a sense of what just like you wrote your child generator function and goal test function, etc. Okay, and so obviously you can only write domains from the point of view of the beginning of the class. You can only write these kinds of domains in explicit knowledge domains. If it is tacit knowledge, you do it, but you don't even know how you do it. You should not be telling computer how to do it. But the surprising thing, as I mentioned at the time of the beginning of the class, is there are enough cases where you have explicit theories of how the world works. We are currently only thinking about cats, for which we have no theories. We don't know what makes a cat. Okay, but how do you, for example, send a rover on the Mars? How do you essentially tell it to pick 4 rocks before the sun goes down? Do you think, after you send a rover onto the Mars, it then basically does reinforcement learning? Right? Right? It's not like, remember for Go, there were 1 million people who were losers who played Go, and there were all these traces. For the same for Dota. There are not 1 million people who went on Mars. There are no traces. There is no data about what to do on Mars. Do you understand what I'm saying? But we have a pretty good idea how to get things done. And so you will essentially, in fact, one of the examples that I mentioned is, NASA people, when they talk about planning, when they talk about mission planning, the kind of thing that rover, Spirit and Rover, Spirit and Opportunity did, is very close to this kind of thing. Because somebody actually knows what the actions are, and it's just that still trying to do put together plans even when you know the actions is very hard. That's what you did in A-star search. You knew what the child generator function is, you know what the goal test is, and yet it takes quite a long time to actually come up with solutions. Okay? So that's the part, so that's the reasoning part. So planning is reasoning. Okay. So this is how the actions look. I mean, there it was in small letters, but you know, when these slides, you can look it up and then it'll look like this. And by the way, you know, right now it's all Python all the time, right? At one time it was the real language as God's intended, which is Lisp, right? And so everything would be in Lisp format. I mean, I can just stop talking about everything else and do one kind of a Jehovah's Witness kind of a list for you guys. It's like the greatest language. But in fact, very many things in Python were copied from Lisp, essentially. So many things from all sorts of good languages were copied from Lisp. And just since we are talking about Lisp, the guy who invented Lisp was John McCarthy, who was one of the 4 people who essentially started the field of AI. He is the guy who gave it the name AI instead of calling it cybernetics. There was a pretty darn good name called cybernetics, but he just hated Norbert Wiener. I mentioned this to you. And so he said, I don't want to call anything that will not make Norbert Wiener start writing papers for that conference. So I'll call it something that nobody will understand. Let's call it artificial intelligence. And so biological cybernetics was actually what Norbert Wiener was doing. In fact, a lot of neural networks research was done in Soviet Union and published in journals like Cybernetica. They will write with K, of course, Cybernetica. Okay, so the message didn't pass to them. They're still, that's why they're not in AI race, because they're doing it in the wrong language. Okay, but anyway, so that's the Lisp, syntax. Here's one other thing, another example of a very small domain, just to give you an idea, one more idea. So this one is actually a one-way rocket domain. Essentially, I have a rocket on Earth. It's obviously a toy domain, and two packages are on Earth, and you want to get both the packages onto the moon, and it's a one-way rocket, and it's actually Apollo 13 too, you notice. So it was very questionable whether it will come back ever or not. So it was a one-way rocket. So the question, of course, is how do you write it as a planning problem? Okay, so you basically can think in terms of the state variables being package A is on Earth, package B is on Earth, the rocket is on Earth. Okay, and then your goal is that A is on Moon, B is on Moon, and actually that's all you actually say. In fact, I won't even write this. I would not even say this. A is on Moon, B is on Moon. And actually, I might say that. So I'll just basically, the goal is that the packages are on Moon. Okay. Now, the interesting thing is, how do you take packages from Earth to Moon? And the reason I brought this up is you can have effects of this type. In addition to just saying, after the action certain variables will be true, I can have conditional effects, which says to get the rocket to go from Earth to Moon, it needs fuel. That's it. But if you are in the rocket when it went, then you will no longer be on Earth, and you will be on Moon. Half of the Warner Brothers cartoons will be, someone, Bugs Bunny, getting into the rocket without the operator's knowledge, and then it's already on the Moon, right? So essentially, the way you get the packets onto the Moon is that you have to put them into the rocket, and then if the rocket takes off, then it'll be on the Moon. And to be able to say that, you write these conditional effects, which says, but if anything which is inside the rocket, after the rocket flies, it will be on the Moon and it won't be on the Earth. You see what I'm saying? Now it turns out the conditional effect is one more of this way of writing things that are in a more compact form. You could take an action like this which has conditional effect and write it into multiple actions which don't have conditional effect. So for example, fly with just A on board would be one action. Fly with just B on board will be another action.
Fly with A and B on board will be the third action. Fly with nobody on board will be the fourth action. And those 4 actions won't need conditional effects. You see what I'm saying? So in some sense, writing this, you can compile it down to those 4 actions if you want. But it's actually useful to have these kinds of shortcuts. Right? So you'll be able to write more complex effects in this case. Okay. So that's basically I wanted to talk about conditional effects. This is a conditional effect. Okay. So conditional effects are of this form. Basically, you write it as the effect from action A. You will say PQR, and this implication sign is not logical implication. It's just a shorthand notation saying that if before A is done, in the state before A is done, if P is true, then in the state after A is done, Q and R will be made. Okay? In addition, you can have an action can have a normal precondition. So if M is not true in the state before A can't even be done. If the rocket doesn't have fuel, it can't even fly. But you don't have to be on the rocket for it to fly. You see what I'm saying? So one is a conditional effect, one is a feasibility precondition. Without that precondition, you will not be able to actually solve the problem. Okay, so it's important to understand that this is about before A, and these are about after. And that's why it's not a real logical implication. Okay, and so that's again a language thing, and so that's what basically is being said here. And then in some sense, I mentioned that thinking of actions in this precondition effect form and thinking of goals in terms of conditions that need to be satisfied has certain amount of naturalness compared to, for example, child generator function and goal test, which are opaque pieces of code. You don't necessarily know when the goal test will say yes, when the goal test will say no. Okay? And similarly, the other one, in another comparison we know, is atomic model reward functions. Reward functions are quite general. But when you talk about goals, when you talk about planning in life, you say I have to do this and this and this. So I have to do 4 things before the end of the day today. And I have the 4 goals. And if I do 2 of them, then I have completed 2 of the 4 things I have to do. Okay? So the goals will have sub-goaling structure. You see what I'm saying? So there are 4 goals, and so you can work on each of the goals in some order until all goals are satisfied. And the other thing is, when you are working on a goal, normally what you would do when you're thinking in terms of planning is that to work on that goal, you would probably put in some action that you will say, oh, I need to get some eggplant, which requires me to go to the grocery store to buy the eggplant. Right? So these actions that have to be put into my, my daily chores now, such that those goals will be satisfied. Right? Now, if I were to have to go to the grocery store, then I might need, basically the action of going to the grocery store might involve taking a car, which itself might have preconditions, such as I have the car key with me, and the car has fuel. You see what I'm saying? So in trying to satisfy some goal, you would put an action which has its own preconditions, which become additional goals now. This is how we tend to think of some kind of planning tasks that we do. So it's not that all planning tasks only have this character, nor is it the case that you can't write planning tasks in reward function model or the child generator goal test model. It is that if you're asking people to give you domain theories, they're more likely to think. You get this one, okay? And because this is how we naturally think about plans and actions. And again, in the simplest case, so if there are n, okay. So in the simplest case, if you have n Boolean variables, n propositions, then there are 2 power n complete states. And for the simplest kind of planning problem, which would be essentially the simplest kind of planning problem would be static world. That means unless you are doing actions, nothing changes. Remember the definitions of environment. And full observability, that means you, the agent, can tell what state you are in. That basically means for you, you can tell, being able to tell what state you are in is being able to tell which of these 2 power n states you are in. And these 2 power n states differ from each other in terms of truth, falsity values of state variables. So full observability now becomes being able to tell whether a state variable is true or false. You see what I'm saying? So sometimes of the n state variables, you might be able to tell that you can sense the truth falsity values of 15 of them, but not the n minus 15 of them. You see what I'm saying? In which case, you don't have complete observability. Neither do you have, you're not blind, but some of the state variables you are unable to observe. Okay? If you have this view, then essentially the simplest case would be initial state is completely specified, values of all the state variables are known. Goal state only needs to tell you what state variables should have what values. So you may not care about every state variable. You just basically in our previous case we said, for example, that I want all the balls to be in room B. I didn't say where the robot should be after the balls are in room B. It could be in room B or room A, I don't care. Okay? Right? So that's the thing, and the goal states are partially specified, and there may be many world states which satisfy goal conditions, just like I said, because this is sort of like the the goal test function might return true for more than one state. And S-star search does allow that, okay? But you are thinking that that's also being allowed in this representation. And there is a natural interpretation of sub-goals and sub-goaling, which is what I mentioned. If there are different features of the goal specification, if you want P1, P2, P3, P4 to be true in the goal state, then you can somehow say, I have 4 goals now. I have to satisfy P1, I have to satisfy P2, I have to satisfy P3, I have to satisfy P4. So one of the interesting questions then becomes, and then so when you're trying to work on the sub-goal P1, then you put in an action and its preconditions now become sub-goals for you. So you recursively work on the sub-goals. It's one way of, you think about planning. So the other interesting question, you basically have a natural interpretation of sub-goals, and this view basically makes you think in terms of sub-goal interactions. Which is, if you have 5 things to do, it's easy if all those 5 things, working on one doesn't take away any resources from working on the second. Right? In that case, you would say sub-goals are all independent. It's an abstraction. Most of the time, the goals that you have in your life,